in our syllabus is this. Let me complete the mechanism first, draw the steps, then I will explain each and every step. Because this mechanism is will be very useful for reactivity order, for explaining reactivity order. Now, with acidified dichromate or acidified chromic anhydride, it will actually intermediate is the chromic acid, which takes part in the oxidation. If I take this primary alcohol with a labeled oxygen atom, it will initially, just after a water elimination, it will initially form this chromate ester. Now, in this primary alcohol, these alpha hydrogen atoms are not acidic. But in this chromate ester, which is quite unstable, because of the strong minus I effect exerted by this OCr-O3 group, these hydrogen atoms, these alpha hydrogen atoms, become acidic enough to be abstracted by H2. So this H2O will then abstract this H as H plus, and this is the rate determining step, slowest step. And it is nothing but an example of E2 elimination by molecular elimination. What is happening actually is H2O with oxygen with one of its lone pair will take this H as H plus. When it is leaving this H leaving as H plus, it is giving its bond pair here. As soon as the double bond is formed, bivalency of oxygen is satisfied. So this is breaking up, this is coming here, followed by the delocalization of this pi bond on this. So in this form, this is from HCrO3 minus, this is H3O plus, and we are getting aldehyde with the labeled oxygen. The aldehyde, we know that it won't stop, primary alcohol, it won't stop at this stage. Aldehyde in water, it will form first this hydrate, unstable, simple addition reaction. Then again with H2CrO4, it will form similar type of chromate ester, which will again undergo an E2 illumination just like the earlier one, and will form carboxylic acid. with that labeled oxygen present in the carboxylic acid and H2O. And same type of mechanism. Now, we have initially said one thing, that aldehydes are more prone to oxidation than primary alcohol. Now it becomes clear why. If we compare between this intermediate 1 and this intermediate 2, we already know why these hydrogen atoms becomes acidic here, because of the minus I effect exerted by the chromate. In this case, in addition to that minus I effect exerted by this chromate group, there is an addition minus I effect exerted by the OH. So this alpha hydrogen is more acidic than this alpha hydrogen atom. So it can be abstracted more easily by water than this. That means this step is much more faster than this, than the earlier one, and that makes the aldehyde more prone to oxidation than the primary alcohol. That's why aldehydes are more reactive towards oxidation than primary alcohol. Now, knowing this mechanism, we can also say why alcohols, I've just erased it, but as I've already shown, since this CH bond cleavage is actually the RDS, that's why the oxidation of alcohol shows hydrogen isotopic effect, because the RDS is the actual rate determining step or the slowest step which controls the rate of the reaction. So summarize the reactivity order of the alcohol. These are the application part actually. Primary alcohol more reactive than secondary alcohol, which in turn is much more reactive than tertiary alcohol. This is very much obvious, because if we go to the earlier mechanism, that hydrogen atom which is removed, that alpha hydrogen atom, is more acidic in primary alcohol, because there is only one plus I effect exerted by R. So primary alcohol actually has more acidic alpha hydrogen atom than the secondary alcohol. Also, in case of secondary alcohol, there will be more crowding in that intermediate. And tertiary alcohol, obviously, the crowding is maximum, so it is least reactive. It can be only undergo reaction, oxidation with a particular reagent, like a very powerful oxidizing agent. Another thing we also have discussed before, this is nothing but summarization of something which we have already discussed. Reason we now know, RCH2H is more reactive than RCD2H, because we already discussed this, alpha hydrogen isotopic effect. R2CHOH is much more reactive than R2CDOH. Now, let us take one question type of thing. Let us take one benzyl alcohol. A paramethyl benzyl alcohol and a para-nitrobenzyl alcohol. It will be 1, 2, 3. If I suppose ask you, or if the question is suppose arrange them in order of decreasing rate of oxidation of alcohols. If you consider in all these things there is a one phenyl ring, so minus I effect exerted by the phenyl ring to this is common. Now what we have to actually find out is in which case this alpha hydrogen atom, this oxidizable hydrogen atom of the alcohol group is more easily replaceable, more acidic. Now if we consider the actual structure, of para-nitrobenzyl alcohol, we already know that this their oxidation or oxidative rate is because of this acidity of this alpha hydrogen. More acidic this alpha, more easily can be removed, more easily it can be oxidized. Nitro exerts a minus I effect. Because of that minus I effect, this carbon will become del plus, and so it will hold the hydrogen atom with less force of attraction, making it much more acidic. On the other hand, methyl will exert a plus I effect because of the plus I effect, this carbon will become less tail plus or more electron rich. So it will hold the hydrogen atom with more force of attraction. This hydrogen atom is much less acidic than this one. So it can be much less much less relatively removed than this one. And this has neither plus I nor minus I group other than phenyl. Phenyl is common. So we can simply say 3 is most reactive because this here the hydrogen atom is most acidic, followed by 1, and least reactive is 2 because here because of plus I effect this hydrogen atom becomes least acidic. Let us take another few examples of the reactivity order, and now we can do on our own, like benzyl alcohol and this. Sorry. Obviously now we know that this reactivity is more because it exerts phenyl group exerts a minus I effect, making this hydrogen atom more acidic. It can be easily removed. Another thing we already have discussed that aldehydes are more oxidizable than more oxidative rate than the primary alcohol. To conclude this part of oxidation, let us take one example. This is actually an application part. Now with CR, suppose we have taken CH3, CH, CH, CH2, CH2H. There is a double bond in the carbon skeleton of the alcohol. With this acidified chromate, or acidified chromic anhydride or acidified chromate, along with oxidation of this primary alcohol to carboxylic acid, there will be also cleavage of this carbon-carbon bond. So we will get a mixture of carboxylic acid. This portion will give acetic acid, and this portion will give corresponding 1, 2, 3 corresponding acetic acid. With Jones reagent, if you remember, Jones reagent won't affect the double bond. It will only oxidize the primary alcohol to corresponding carboxylic acid. So this double bond remains unaffected, unlike the earlier case. With PCC, again it won't affect the double bond, but the primary alcohol can only be converted to corresponding aldehyde. So we will get this one. We'll get this one.